Good afternoon, guys. I hope you're doing well. Let me just make sure that I'm actually recording because if I'm not, then I'm going to be in trouble. Okay, I am actually recording. Sorry, I've made a mistake and not recorded a couple of times. All right, so we're back to talk about sig figs. Now, if you're comfortable with sig figs, you may not want to hear all of this. I get that. But we are going to do some talking about why they're significant and what exactly that means. And that might be information that's relevant to you because you may not know exactly why that is. You may be comfortable with the math part of working with sig figs, but you may not know exactly why they're significant or what they're for. And so that's going to be here at the beginning. Okay, so why do we talk about this? Well, almost everything that we do in chemistry is based on the measurement. It's based on some piece of data that somebody went and collected. And for reasons that are very obvious by looking at these rulers, we don't always have the best tools available to do that. Sometimes we have the best tools, sometimes we don't. If we had the best tools all the time, it would always be, an infinite number of decimal places that we would know this to. But usually we have to make a compromise between how many sig figs we can get and how much money we can or are willing to spend for that piece of equipment. There's a direct correlation there because the more decimal places you can get, the more expensive that equipment has to be able to give it to you. And the more maintenance you have to do to keep it set the way it's supposed to be set. I think the easiest way to talk about this is in something very practical, something that we deal with all the time, and that's rulers. Okay, so I want to measure a paperclip. I want to know how big that paperclip is. Silly thing to do, yes, but it's an easy way to talk about that. If I just have a centimeter ruler, so it's only measured in centimeters, then looking at this paperclip and only looking at that first ruler, I can see that it's more than 2 centimeters. It's less than 3 centimeters. Okay, it's at least 2. So I'm going to write down that 2. Because I know it's at least 2. Because I can see that it's past this line. And it hasn't gotten here. So it's got to be something in the 2s. Now, I can look here, and I'm not going to look over here because I don't want to know any of the rest of this. I can look here and I can say, okay, it's more than 2.5. It's kind of close to 3. And my gut says 2.8. Now it could be 2.75, it could be 2.7, it could be any number of those things. I don't know, so I have to guess. And that's the point. We're guessing. So we always know the numbers that are marked on the ruler, but then we have to guess the next one. We are expected in the lab to report the next one that we're estimating. For anything where we can estimate it like this. Now on a balance, I can't do that. The number that it gives me is the number that it gives me, and that's all I can do. If I have something like this where I can estimate that. Burettes, pipettes, things that measure volume, we can do that. Okay, for some of those things. And burette is the most common place for us to see it. Because other places we tend to use volumetric glassware, and it's exactly measured. But if I'm using a graduated cylinder, I may have to guess. Okay, now I can do my best and I can spend 20 years in the lab to get it exact so that I can report that number. Sure. But if I'm going to spend all that time to get it exact, I better report all of those decimals to show that I did that. Okay, that's important. All right. Now, I guessed that point whatever. So that's the number I report, 2.8. And of course, this is in centimeters, so I say 2.8 centimeters. Since I know what the unit is, I need to put the unit. Talk about that more later. If I look at the next rule, I'm still measuring in centimeters, right? It's still looking at the same kind of thing. And I'm like, okay, all right. What do I see here? Well, again, I can see that it's past 2. I can see that it's past 2.5. And I knew that before. And it's not to 3, so it's 2 point something. And I knew that before, and I still do. But now I can look and I can see that it's above the 2.5 and it's 2.6, 2.7. So that's one thing. I know it's 2.7. And then, of course, I have to look at the where it is and say, is it exactly 2.7 or is it slightly above or slightly below? Is it exactly that? And to me, that looks like it's exactly 2.7. And so I'm going to report that as 2.70. So I measured the 2.7 and I estimated the 0. So it's one decimal past what's actually marked on that ruler that I'm estimating. We always know that the last digit that's present is an estimate of some kind. Okay. What you'll see if you're actually working on a balance in the laboratory, there'll be fluctuations in that last number. And that can be due to air currents, it can be due to people walking past it, it can be due to, how much electricity your watch gives off. There's so many things that can do that. And so you'll see that there's variation in that number. And that means that it's still an estimate. Okay, so that last number that we report is not always that well known. And so it's our last estimated number. Okay, that becomes important when we're talking about sig figs. Because if I were to talk about the number of sig figs that these things have, I know that this one has 2 sig figs. Because both of those are non-zero, right? For reasons that we'll talk about in just a minute, this one is 3. And why do I know that it's 3 sig figs? Well, that's a really interesting question. And that's because these two are non-zero, so I know there's a significant. And this one, I had to guesstimate from that ruler. So I know it's an actual number that's significant because I estimated it. So I bothered to write it down. That's because it was significant. And I know that it's roughly that number. And so the fact that I bothered to write it down indicates that it is a significant digit. What this means to you is if you see that it's 2.7, it is inappropriate for you to report this as 2.7 centimeters. That is inappropriate because you have left off a sig fig. Okay? You need to make sure that you understand that. The numbers that you're getting, even though you haven't measured them, have been measured with similar types of things. And so those numbers are significant because of how they were measured. So that's why they're important. That's what we mean by sig figs. That's why they're important. Okay. So we always estimate, that's what this says. Some things are more precise than others. And we'll talk about precision versus accuracy next lecture. Okay. We will come back to this. And we can only pretend that our numbers are at least as precise as the least precise number that's measured. Okay. So if I'm working with a calculation that has this in it, has 2 sig figs, versus a balance that gave me 6 sig figs, then the number that I calculate can only be 2 significant digits because that was the least precise known, so that limits it. Okay. So that's what we've got for that. Now we'll talk about the rest of the details of the math parts in just a few minutes, but that's why this matters. Okay. Now, I'm going to take just a second to look at something. I apologize. I want to check something I did. Okay. Okay. So that's what sig figs are. I'm going to break here. I apologize for the leaving the extra time in there, but I'm going to break here. So I'm going to stop sharing and I'm going to stop recording. So if that's the only part you wanted to hear, you're done. All right. And then I'm going to go into how we deal with those numbers. And just, well, no, actually I'm not. Never mind. Sorry. I see I can't make up my mind. Isn't this great? Let me share again. So I changed my mind. I love it. So now I'm going to come back and talk about what numbers are significant. So I talked about the why of that there's why they're significant. Now let's talk about the what. Okay. Which of these numbers? Any non-zero digit is significant. Anything that's not a zero is significant. That's just how that works. But what about the zeros? sometimes they are, sometimes they're not. If I have a zero that occurs between two non-zero digits, it's important. Because if this zero wasn't there, then that would look like 11. That is not the same number as 101. If these two non-zero digits were not here, that would look like 11, and that's not the same. You see what I mean? So those placeholders in the middle are important. So those are significant. That's why I have 3 sig figs here and 4 sig figs here. Okay, so that we've got. But then we have to talk about our zero situations. Okay, if the zero comes before the non-zero digits, then it's a placeholder. It's just to tell us that it's a number smaller than 1. You know, it's just a placeholder to tell us that that number is, millimeters versus centimeter versus meters, that kind of thing. So it's small. So those are not significant. So the zeros are not significant. Hence, all of these numbers have 1 sig fig in them, all of them. Now, if I were to write this in scientific notation, which is one of my lovely things that I can do, I would take the decimal place from here, 1, 2 places to get it where it is. So it's 1 times 10 to the minus 2, because that's how many places I moved it. This would be 1 times, and this one, 1, 2, 3, 10 to the minus 3. And this one is just 1. And if I wanted to report that as 1 times 10 to the 0, that would be appropriate, right? Because that does just mean 1. So scientific notation for those, all of them have 1 significant digit. Awesome. Well, what if the zeros are at the end of the number? Well, we can't just say that none of them are significant. And I hope that it's now obvious to you why that is. Remember, we talked about that number being 2.70 and that number at the end mattered because I bothered to write it down? That's true. So if those zeros are there and they're after the decimal place, they're there to indicate that we know that number to that decimal place, but it's a 0. So we have to have them. So this one has the 2 sig figs, this has 3 sig figs, and this one is only 2. You see the 2 red ones are the zeros like we talked about before. So I could put this into scientific notation, and I would report that as 1.0, those 2 numbers right there, times 10 to the minus 2. Okay, so only 2 sig figs, and it's the 2 that are reported right there. We can talk about this one. Now, I talk about this because it's one of my favorite things, and my kid goes to football games at the high school, and they say, "Oh, well, there were 300 people at the game." Okay, did somebody actually stand there and count 300? Did they use a counter and count them off, or did they estimate that? It's a good question, but without asking questions, I won't know. Okay, I can assume that it's an estimate, or I can assume that it's accurate, but that is an assumption. We all know what happens when we make assumptions. Okay, so to make it clear, because I usually can't ask, I have to put the decimal place in if it's exactly known. So if I counted all of those people and it was exactly 300, then I need to put the decimal there. And that's what this indicates. If the decimal is present, then that number and all of the zeros between the number and the period are significant. If it's an estimate, we would just write this as 100, and that would be 1 significant digit. Okay, which is what we see right below it. Okay, this is only 1 sig fig. All right, and what it says is, in such a situation, I can turn that into scientific notation. Well, that's great. I mean, that's absolutely fabulous. But how do I do that? I mean, do I have to sit there and count with, like I was doing? Because it's kind of painful to do that. So is that really what I need to do? Well, I choose not to do it that way. Let me put it that way. I choose not to do it that way. All right. One of the things that I can do, and I want to talk about, which number did I want to talk about? That one. So I'm going to take the 0.010, right? And what I'm first going to do is say, okay, I'm going to put my calculator into scientific notation mode. So I go to second and I go to mode. Oh, actually, I didn't want the second. Sorry, I just need to click mode. And notice that I'm on the second line. It says normal, sci, and engineering. Not all of them are in the same place. But what that tells me is I can look at a number in a normal format. I can always report a number in scientific notation, or I can report it in engineering notation. I'm not really sure what that means because I'm not an engineer, so I'm not going to guess. I'm going to put it on sci and hit enter. And that means I've chosen scientific notation for this calculator. And it's not going to report everything in scientific notation. Now I can do a second quit. And it doesn't look any different right here, but if I take 0.0010 and I enter that, I get 1 times 10 to the minus 3. One thing I have to point out to you, and this I hope is really obvious. We just talked about the fact that this number 0.0010, which is not exactly this number, is 1 times 10 to the minus 3. But when we talked about this one, we said that it had 2 sig figs, and this answer that it gave me is 1. My calculator does not understand that I needed to have that number of sig figs. Now, if I'm not on a test, I work in Excel. Excel can be told how many sig figs to keep, so I can do it there, and it makes my life a lot easier. But I need to understand that even though it's reported as 1 times 10 to the minus 3, the number that I have to write down on my piece of paper is 1.0 times 10 to the minus 3. And that's the same as 0.0010. Okay, so those are the 2 ways that I can report that number. So turning it into scientific notation should tell me how many sig figs it has, unless there's a 0 at the end. Okay, but it'll tell me how many, whether or not I can get rid of the ones at the front. All right, so that's helpful to me. Not always helpful, but it's helpful to me. And that's how I put it into scientific notation. And if you need this calculator out of scientific notation, you just go back to mode and you see that it's sitting on this line, normal, sci, and engineering. It's over the normal now, so I hit enter. And then I say second quit. And I haven't done anything, so I say, well, take that number that I just had and multiply it by 1, because I want the same, and it's 0.001. So it's back in normal notation. Now we've lost that 0 at the end. Again, we just talked about that. But now I can see that I can get back. And for me, I often do this. So I'll put it into scientific notation, multiply my answer by 1 to see what it looks like in scientific notation, or I'll forget to take it back out and then need to get it back into the normal format, and so multiply it by 1 to do that. Okay, so that part I'm going to show you there. Scientific notation is something that you can do as far as mode goes on your calculator. So that part we've talked about. We'll talk about it again a little bit later, if you choose to watch that part. So, again, talking about this in terms of scientific notation. This is 1 sig fig, this is 2, and this one is 3. Okay, so don't forget that those ones past the decimal place are important. Okay. So we just talked about the rules for sig figs, right? I mean, we talked about everything, didn't we? We talked that non-zero numbers are always significant. That's the first one. We got that. Zeros between non-zero numbers are significant. I got that. All final zeros to the right of the decimal place are significant. I got that. Placeholders, zeros are not significant. To remove them, I put it in scientific notation. I figured that out just a minute ago. And so here's 4 simple rules as opposed to what we were looking at before. But now there's this 5th rule. Oh, wait. Have we talked about this? It says counting numbers and defined constants have an infinite number of significant figures. Okay, well, that's awesome. Huh? What we mean by that is, let's just say that we're going to try and calculate a molecular weight, and I need to know how many carbons are on this particular molecule, and there happen to be 4. So I'm going to take 4 of them and multiply it by this mass to get my total mass from carbon. Okay. Now, all of those numbers may or may not make any sense to you at this point, and that's okay. Notice there are no units on them. That makes me very uncomfortable, so that's why I mentioned it. But this 4 that's out here does not determine how many sig figs my answer should have. That is determined by the mass that I'm given. So that number that I have that I've written as 12.01, That will determine how many sig figs I have. The counting number is not considered. And that's what we mean by the counting numbers, because I counted the number of carbons to get that. Okay. Defined constants have an infinite number of sig figs. So defined constant that most of us are familiar with is pi, right? And of course, we can report pi to God knows how many decimal places, and I know that there are people who can do it, but frankly, I have never, and I don't want to. So I normally report pi as 3.14, and occasionally I'll do 3.1417. Okay, that part you know. That's a different number of sig figs. So do I consider those? No, we don't. Defined constants, no matter what they are or how they are reported, even though if I know there's more numbers that go after it, we treat them as if they're infinitely significant. Okay, as if they were exactly those numbers and they were a counting number, and we just deal with it that way. So we don't use the number of sig figs in our defined constants to determine the number of sig figs our answers should have. Okay, so make sure that you remember that defined constants are not what we use to count to determine how many sig figs we've got. It becomes more important later. We'll talk about it again later. So this will come back again, actually a couple of times, but there you go. So that's our other rule that we need to talk about. So that's my sig figs rules. So that's how I know what's significant. Now we got to talk about this rounding, because if not all of my numbers are significant, and then I do stuff with them, then I need to be able to round. So let's talk about this for a second. So we just talked about that locator zeros are, special. They don't count. So 0.0032 and 12,000 both have 2 sig figs. So 2 sig figs in those numbers, because only the 3 and the 2 and only the 1 and the 2 are significant. When we do math with any numbers that have sig figs in them, there are 2 ways that we handle them. One is the addition and subtraction, and one is the multiplication and division. Those are different things, and they have different rules. For addition and subtraction, the least number of places to the right determines it. And the most obvious way for me to talk about this, to help you to understand it, or at least the way that made it the most sense to me, was to write it down like this. 189.2. And then I'm going to add, actually, let me get them in the order that they gave them to me. So 1725.463. And then I'm going to add 189.2. And then I'm going to add 16.73. And if I do that lovely addition, I end up getting 19, at the right place, 1, 9. I thought I erased that. Thank you. 1931.393. So when I put all this in my calculator, that's what it spits out. But hold on. Remember we talked about the fact that we have a different number of sig figs in all of these numbers, right? So here I have 3 past the decimal place, I have 1 past the decimal place, and here I have 2 past the decimal place. Now the total number of sig figs in each of these numbers is important. This one has 4, this one has 4, so that's 4, that's 4, and this one is 1, 2, 3, 4, 5, 6, 7. But for addition and subtraction, I don't care how many there are. It's not important to me how many there are. It matters how close to the decimal place they are. Because I know this one a lot better than I know this one. So when I add this number together, I can't pretend that this is exactly 2.00 because I don't know that it is. So I have to limit my answer to the same precision which I knew my numbers. And so it's limited by this place right here, because that's the only one that I have a number in all of them. So my answer gets reported as 1931 point, and it says 39, so I don't just report it as 3. I have to round that up because the next thing is a 9, so I round that to 0.4. 1 decimal place, because that's the least precise number in that I'm using. Okay? The closest to the decimal place. So that's where that comes from. So that's one of them. The other thing we do is multiplication and division. We do this the most often. Now, remember, when we talk about calculating molecular weights, those are counting numbers. So we have 4 carbons. We don't consider that as part of this, right? So that's one thing. And it's actually an addition that we're doing. We're doing that number 4 times and adding it together. So we can multiply by 4 rather than doing the addition 4 times. Here, I'm trying to multiply 0.1742 times 0.216 times 0.0013. And if I put this into a calculator that's capable and willing of showing it, this is the answer that it spits out. All right? That's awesome. That's a great number. It has 1, 2, 3, 4, 5 sig figs in it. The numbers that I started with, there are 4 there, there are 3 there, and there are 2 there. And so I can't just magically have 5. I didn't have 5 to start with. So even though I've done this multiplication, that doesn't mean that I can just add significance to it. That's not how that works. And I have to be limited by the number of sig figs I had in the least precise number, which is the one that has 2 sig figs. So my answer has to be reported to 2 sig figs, which means that I'm going to take and round this number, and that means I'm going to go, and it's right there, but 0.0000, and then it's a 4. That's my first non-zero digit. The next thing past it is an 8. So my second decimal is 4, and it's 489. So I'm going to round to 49. And that's how they get this number that they have right here. Now, that's awesome. When I do this on my calculator, it spits out an answer in scientific notation. My calculator always does, no matter if I'm in normal mode or scientific mode. So I can report that too. That's fine. I don't care how you report it. Doesn't matter. It just needs to have the right number of sig figs. Okay? So that's important. Now, exact values don't count. This is that 5th rule that we talked about there. So 2.54 and 12 are both considered to have infinite precision. So 2.54 is a conversion factor from centimeters to inches, 12 inches per foot. So conversion factor there. So our conversion factors and our counting numbers we don't use for consideration of number of sig figs. The last thing I'm going to tell you is it says round after calculations. So I do calculations, right? And I do this one right here, and I do the multiplication because order of operations. So I do multiplication first, 3.24 times 1.96. And that gives me this, my calculator spits out 6.3504. And then I multiply 2.56 times 2.48, and my calculator spits out the 2.3488. Okay. Then I do the subtraction, right? And that means I'm looking at how many decimal places are past how many places past the decimal point. Both of them have 4. So my answer needs to be reported that way. That's how I get that 0.0016. Okay. So what I didn't do is I didn't round this number right here to the 3 sig figs that I could have rounded it to. And that's because I don't want to do that until the very end, because if I do that, I end up with something called rounding errors. And that's what we mean by this accumulation of error. So if you're asked to report a mid-value on a test, because sometimes I'll do this, and I'll ask you to report this calculation, you report it as the right number of sig figs, but then when you use that number again, you don't want it rounded when you do it. Okay? So do all of your calculations before you consider your sig figs. Now, this assumption that is written here is here because I stole this from someone else. I can't remember where I stole it from, so I cannot give it proper credit, which means that I'm going to have to redo this on my own sometime. But we are not going to assume the 3 sig digits for this class. Now, what does that mean for you? And I've said that we're not doing that. You need to figure out how many sig figs should be on your answers. Since I can't stand and watch you do all of your calculations, Alex is going to do that for me. And it's going to say, that's the wrong number of sig figs. By the time you're done with that, you should have a better idea of when it's significant, when it's not, when to round, when, all of the nuances of those things and these rules and should be pounded into your brain. Okay, so it shouldn't be that hard when you get to the test because you've done all ALEKS homework. All right. So it will grade you on that in ALEKS. And when you get to the test, what do I expect? I expect to see your work, and I expect to see it reported to the correct number of sig figs. It needs to be the right number of sig figs. You need to be doing it. That needs to be your practice. It should be what you're doing every time. But I only grade one question for significant digits. That's the one I'll take points from. And a sig fig error is 1 point. If you get it wrong and you report too many or too few, that's going to be an issue, and I'll take a point. We call it the sig fig tax. Does that mean it's insignificant? No, absolutely it doesn't. But it means that you're getting penalized for it other places, so I'm not going to bother to do it there. And here's the other thing. I am not going to tell you in advance which question is going to be graded for sig figs, because I honestly do not know. I will choose one as I'm grading. So as I grade the tests and I get a feel for where people are messing up sig figs, that's usually where I do it, because I have an opportunity to show you why it's not what you thought it was. Okay. Do I do it on everybody's test the same way? Yes, I always pick the same one. Every test will get that, but it's reflective of how the class was doing as a whole. Okay. So there's that part. That's the rounding. And this lovely next slide, I love this slide, and I wanted it, but and there's a bunch of information on it that I didn't really want, and I was too lazy to modify it. So here you go. Here's the parts you actually need. So why did I do this? Why is this? Why? Because I wanted to remind you that addition and subtraction are done to the least precise decimal place. You've probably heard that wording a few times as we've been talking about this. And again, you may not know exactly what we mean by precise, but you know it has something to do with how many decimal places there are. Okay, that's true. We'll talk about the definition of that in the next lecture. All right. Multiplication and division are to the least number of sig figs. That's the whole reason that this is here. And granted, I should have done it in a different format. I understand that. But remember that addition and subtraction is one set of rules. Multiplication and division is a second set of rules. Okay? That's my whole point in having this here. Now, we're going to talk about rounding, and then we're going to take a break. So what are my significant figures rules of rounding? Now, there's one thing in here that this statement, I have read this I don't know how many times, and I cannot figure out what they mean by it. So I'm going to ignore it. I'm going to tell you not to pay attention to that. Because one, I don't understand what they're trying to say, and two, I don't agree with whatever it is that they're trying to say because I don't understand it, which means that whatever it is, they didn't teach me that. So that's not how this works. Okay? All right. Now let's talk about this. If the digit immediately to the right of the last significant figure in my number, so if I need to round 56.87 to 3 sig figs, then I'm going to report that as 56.9 because that 7 is greater than 5, so I'm going to round up, and that means 56.9. If it's less than 5, then I'm not going to change the last digit. So if I have 2.02, I'm trying to get it to 3 sig figs, that's 2.0. So above 5 goes up, below 5 goes down. And this is how I write that. So above 5 goes up, below 5 goes down, arrows go the same way. Okay. But what about if that number ends in a 5 and there's nothing after it? So I'm trying to round, and the number that I have is 2.835, and I need to round it to 3 sig figs. What do I do with that? Because it's 5. So does that mean I round up? And it doesn't. I did not say above or equal to. I said above 5. So when it is 5, if the number that's after it is even, we do one thing. And that's the second one. So I'm going to move this. I apologize. If the number after it is odd, we do one thing. And if it's 5 and the number before it is even, we do something else. So there's no number after it. So now I'm looking at the number before it. So 2.835, the number before the decimal that I'm trying to round is 8. Oh, 3. Sorry, I'm looking at the last part. So 2.835, I'm trying to round that 5, get rid of the 5 part. So since it's an odd number, I'm going to round up to 2.85. So if it's odd, it goes up. If it's 2.65, and I'm trying to round to the point, whatever. If it's exactly 2.65, the number before the 5 is 6. That's an even number. That number goes down. Or stays as, well, actually stays as it is. It's not really going down. It just means that I'm not putting it up. That's what I mean by the down arrows there. Okay. Why do we do that? Well, okay, let's think about this for a second. If I have a whole bunch of 5s and I have to round them all, and I do it the same way every time, that leads to an inherent bias. Okay? And that bias is going to be a problem for us. We have to try and make sure that we're not introducing bias into our numbers and into our calculations. But I, as a human being, cannot do it. We all have mathematical biases, and they have a lot to do with our cultural upbringing and, how we look at the world. And, there's a bunch of stuff in that, okay? Not least of which is this whole odd, the word odd, and how we feel about the word odd. Most people don't want to round don't want to have odd numbers, and so they want to get rid of it to make it even. Okay, so when they see odd, even though they're rounding a different decimal, they're always going to try and round up because they want to get rid of the odd. But we can't have that kind of bias because it leads to problems. And that's why we have to do this when it's exactly 5. Sometimes we go up, sometimes we go down to try and minimize that bias. Okay, and to try and make it not based on who we are, but based on the same set of rules as everybody else has. Right? So 2 people will report the numbers the same way. That's what we're looking for, is consistency. So hopefully there are no questions about that. I know that this is probably, we probably knew this part before. Familiar. And this part is new. So the new part should become much more comfortable to you as you continue to work with the problems in ALEKS, and it beats you up about the sig figs. Okay? Now, it does say that I'm supposed to stop here, so I'm going to stop sharing, and I'm going to stop this recording, and I'll see you back in a few minutes.